if you're new here, this is the Young African Scientist platform, and you are welcome. If you have not registered yet, then go to our website, that is yaslinkup.com, and you would see the engine there and you can register there. I'll also post the link for registration in the chat box. So if you have not registered, you can register as well. And we have already done a lot of videos. This is our fifth lecture, and we have looked at the introduction to machine learning. We have looked at introduction to Python. We have 2 classes in Python. Then we looked at data science, introduction to data science last week. This week, we are looking at feature engineering. This is a very important part of machine learning, where you begin to assign certain features to your data and you reorganize your data. So this is very important. And we have one of our PhD students who has been with us for a while. She's been doing a lot of feature engineering and feature importance work with machine learning. And so she's going to take this class today. So I'm going to pass you over to her. Bernice, are you around? So she will introduce herself. She will share her slides. And Bernice, please send your slides to me so that I can push it to them as well. Yeah, so you're all welcome. I'll pass you on.
I think
Yeah, so I'll pass on to Bernice and for her to take over the class and for her to start. So Bernice, please take over if you are ready.
All right, sir. Thank you very much. All right, so I'm Bernice Abraham, and I'm here to take this lecture today. Let me quickly share my screen before I start.
So as she prepares, let me do a few housekeeping rules. I'll be posting the attendance link in the chat shortly. So please, every one of you should go in there and let us know you were present today. It's a very important exercise because it determines who gets your certificate and who doesn't get it. And so please go in there and just click the link and just mark yourself present. If you don't have your Young African Scientist professional code, send me a private message. I'll check through the database and get your code to you. But you can still register using your email in place of your professional code. And so please register without, mark your attendance without any restrictions for us. Thank you. Bernice, please go ahead.
All right, thank you very much. Okay, so the topic for today's class, as has been previously introduced, is feature engineering and evaluation metrics, and I'm Bernice Abraham. So I'm a PhD student on the RSIF facet, currently placed for my IPI at SUNY Polytechnic Institute. So is my screen visible?
Yes, it is.
Yes.
All right. Thank you very much. Okay, so this is actually the outline of what we're going to be looking at today. First of all, the topic, as we have seen, is feature engineering. But during our last class with Dr. Trustin, we actually started doing feature engineering last class. For those of us who were present, we started doing feature engineering. And I'm going to briefly explain what that is and how it relates to what we're going to do today. So, sorry, let me get my pointer. All right. So this is what we're going to be doing. We're going to look at some evaluation metrics. We're going for classification, like we learned before. Machine learning, we have both classification under supervised learning. We have classification and regression. So we're going to look at how to class, how to evaluate your model. How do you know that your model is performing well? So going back to what we did last week, during last week's class, we looked at ways of improving our features. You have a data set that you want to use to create a machine learning model. So we looked at how to clean up the features. We looked at principal component analysis, how to scale the features, scaling, normalization. All that is actually feature engineering in a way to improve your data such that your data is good enough to be used to create a machine learning model. So we looked at that last class. So this class, what we're actually going to be looking at in relation to that is feature selection. Now you have created the right features, you have cleaned your features, you have made sure that they are good enough for your machine learning model, and then you now run through your model. Okay, after running through your model, you're going to be able to have to evaluate your model to see whether your model did well. And then after evaluating the model, you now have to find a way of improving the model's performance. And that's where feature selection comes in. When you evaluate your model and you see that there's room for improvement, it didn't perform as well as you expected it to, then you may have to select the features that are most important or more relevant for the performance of that model so that you can have a robust model that will give you the kind of results that are very that will give you good and important results. So before we look at feature selection, we need to be able to know, how do we evaluate our models? How do you know that your model is performing well? And that's where the evaluation metrics come in. So looking at our outline, the first topic is for evaluation metrics for classification. We're going to be looking at the confusion metrics, precision, recall, F1 score, and accuracy. Then if you're doing regression, the metrics will be looking at the mean absolute error, mean square error, root mean square error, and R squared. Then we're going to be looking at what we call overfitting and underfitting. Then we'll look at how to split our data to run our machine learning models. Then we'll look at feature selection and feature importance. Then dimensionality reduction, which is still part of the feature selection. And then we'll actually go through training a simple machine learning models and see how all these things that we have looked at, how they actually look practically. So like I mentioned earlier, under supervised learning, we could either have a classification problem or a regression problem. And we know under classification, you are trying to actually you are trying to predict categories, right? Is this yes or no? Is it your email spam or not spam? You're actually predicting categories. It could be 2 categories, it could be 3 categories, but that's what you're looking at. But with regression, your output is usually a continuous value, like figures. We have examples here, like predicting prices of houses, like we looked at in one of the data sets that Dr. Trustin shared last week. So those are continuous variables. So we use regression models for such kind of problems. So today we're going to look at evaluation metrics for both classification models and for regression models, how we can tell whether our models are performing well. This is just an overview. So we have done data processing before. So we'll look at how to evaluate our model, train a model, and then look at how to do feature selection. So now looking at classification evaluation metrics, the most common evaluation metrics for classification, which most of us should have heard about, is the accuracy. Then we'll also look at the confusion matrix, which is also very common. And then we'll look at precision, recall, and the F1 score. Then we'll look at the receiver operating curve. And we'll try to give an overview so we can understand what this means. And when we get them, how we can interpret them to know whether our model is performing well or whether it needs small improvements. So accuracy, that's the first evaluation metric we're going to look at. And this is for classification data. So remember, in classification, you're trying to, your output is either of 2 or 3 classes, right? Your yes or no, those kind of categorical values. So accuracy actually tells us how many correct, it gives you like the percentage of how many correct predictions your model is able to make, very direct. So you can see the formula for accuracy here, number of correct predictions over total number of predictions. So out of the predictions your model was able to make, how many of them were correct? So it's a simple percentage. So it's actually the most popular metric but it is not enough to tell you how well your model is performing. So, for example, your data set, if you have a data set that has maybe two classes, right? And then one class is 80% of the data, and the other class is maybe 20% of the data, your predictions may most likely have a high accuracy, because since one class is more than the other, the accuracy will definitely most likely be high, because it will be easy for the model to predict class A. So you have a higher accuracy, but it's not enough. We need other models to be able to tell us how well other metrics to be able to tell us how well the model is able to distinguish between the different classes. And that's where we come to the other models that we're going to look at, because sometimes your data may not be so balanced. Though last class we looked at how you could try to create a balance in your data, but in the real world, when you collect data from databases or you go out and do some experiments, you may not have a balanced data set. So you need to be able to tell if your model is distinguishing between the classes very well. And then that's where the other evaluation models come in. So the accuracy is actually a good evaluation metric. It's the most direct, easy to interpret. It's very easy to understand. And actually, no matter how imbalanced or your data set is, it's very good to have a high accuracy, but it's also good to have the other metrics to also be high. So let's move forward. So the next metric, which is also quite common, is the confusion matrix. The confusion matrix now gives you more details about how well your model is able to do predictions. Now let's look at this plot here on the right, or rather on my left. So a confusion matrix actually plots your actual predictions, the actual values, that's what was actually in your data set, versus what your model predicted. Now, if we look at this green box right here, we have true positives. That means in the values you get within this box, like what we have in the blue box here, we have 12. That means these 12 values here were actually true. They were true in the actual data set, and the model also predicted them to be true. This is a confusion matrix which I just extracted from one of the data sets from the work we're doing. So you can see that in this case, at this upper corner here, upper left corner, we have 12, which means that you actually had these 12 values were true, and the model also predicted them to be true, which is good. If you come to the bottom right corner here, we have 19. Here we have the model predicted 1 here, and they were actually 1 in the data set. So this is good. So when these boxes in the diagonal here have a high value, it's actually very good for you, because the model is doing well. So here we have class 0, and the zero. Meanwhile, the actual data is supposed to be 1.
Denise,
So the model
Denise, we lost
here.
you for
In
a
this
while.
particular one here, the upper, yeah. Can you hear me?
Yeah, we lost you for like 2 minutes. So just go back a little bit. When you presented under 1, and you said when the 2 boxes are filled, it's very good. Start from there.
Yes. Okay. All right. So I was saying that when you have this diagonal going up towards the left, when you have this with high figures, it's actually good, because your model is predicting rightly here. But when we have this diagonal now going up towards the right, you wish to have fewer values here because this shows where your model is failing. Now, from this data set, in this work, we're actually trying to predict two classes, 0 and 1. So you can see that in this lower box here, we have two classes where the model predicted 0 when the values were actually supposed to be 1. This is a failure on the part of the model. And then the upper one here actually has 0, means the model did not fail in predicting here. But you don't want to have so many values here. When you have so many figures here, then it is reducing the accuracy of your model will actually drop. You can, if you have data, if you can maybe compare accuracy with confusion matrices, you will see that as the accuracy is dropping, you see that the values here will be increasing and this will be dropping. So you want to have less values in this diagonal and more this way. So this shows you can actually see clearly how well your model was able to predict between the true values and how well it was able to give you either false positives and true positives. So what are actually false positives? I explained that in the next slide. Now, false positive is actually called a type 1 error. This is when the model tells, the model is actually giving you a positive result when it doesn't exist. So you can see this man here, and the doctor is telling him that he's pregnant, right? Meanwhile, it's actually impossible for him to be pregnant. So this is a false positive. It is called a type 1 error. And then when the situation actually exists and the model says it doesn't exist, that's a false negative, and it's called a type 2 error. So your confusion matrix actually gives you how well your model is able to distinguish between false positives, false negatives, true positives, and true negatives. Now, another metric that can actually help us understand that better is when we come to the precision, recall, and the F1 score. And we're going to look at that now. So for precision, now, precision is giving us if you look at the equation here, the first equation here for precision, it tells us out of all the positive values that your model gave you, all the positive predictions that the model made, how many were actually true? Because when you do your model and you run, you get predictions. Out of all the positives that the model was able to tell you, how many were actually true? So you're looking for the percentage of true positives out of all the positive results that the model gave to you. Now, in a situation where having a negative result is very fatal, for example, if you're trying to predict like diagnosis, having a negative result is very fatal because if you predict negative for like a very serious ailment, then you are letting somebody go when the person is actually maybe terminally ill. So in a situation where having a negative result is going to be very detrimental, then you want to have high precision. So your model should be able to give you a high percentage of true positives. So once again, precision tells you out of all the positive values or positive results that your model predicted, how many of them were actually true positives. Then for recall now tells you out of all the predictions that the model made, both the true positives and the total predictions the model made, how many were actually true. So there are metrics that you actually have to balance. The model has, when you have both of them reasonably high, it tells you that your model is very good at distinguishing between positive and negative values. So you want to tune your model such that your precision and recall are reasonably high. And the metric that also tells you that your precision and recall are okay is the F1 score. The F1 score is kind of like taking some kind of average of the precision and recall. So you want your model to have a balance between precision and recall. And when you have that good balance, your F1 score will be high, which is good for every model to show that the model is actually able to distinguish properly between true values and false values. So you could have a model that gives you a high accuracy, but F1 score is low, this tells you that maybe the accuracy is just because maybe one class is far more than the other classes. That's why the model was given high accuracy, but the model itself is not able to distinguish between the positives and the negatives, or between the classes that you have. So you want to tune the model, and that's where all the other things that we have learned, and we are also going to learn in the coming classes, will help us how to tune our models, how to do the scaling, normalization, all those things we need to do, such that we can create a balance so that our accuracy is high and our F1 score is also high, to show that our model has good distinguishability. All right. So another metric which can be used for classification is what we call the receiver operating curves. Now, this particular metric, it just plots the true positive rate versus the false positive rate, as we can see here. These are also some plots are extracted from our data. As you can see, when the model plots this true positive rate versus the false positive rate, the AUC is called area under the curve. It actually calculates the area under the curve for you. Now, if you look at this first plot here, we have the area under the curve at 0.95, which is a very good area under the curve. The closer it is to 1, it shows you that your model is good at distinguishing between true positives and false positives, actually giving you good predictions. But once the area under the curve is low, at 0.5, it's kind of like a random guess. When you have an area under the curve of 0.5, it's like your model is just guessing. It's not really doing any good prediction. So you want to get the area under the curve to be as close to 1 as possible, to show you that your model is actually distinguishing properly between your classes, or between positives and negatives, or however many classes you have, whether 2 classes, 3 classes, 4 classes. It shows you that your model is actually distinguishing very well, and that is good for a classification model. So all these metrics we have looked at are metrics that will help us when we are doing classification, to be able to tell whether our models are performing well, and then can help us also figure out what we need to do to improve the performance of the model. So we now move to regression. Please, if there are any questions, you can post them in the chat, and then I'll attend to them as we progress. So for regression, which we remember that regression, we have continuous outputs with regression. Your outputs are continuous values. So the metrics for evaluating regression are different than the ones for evaluating classification. So we're going to be looking at the mean absolute error, mean squared error, root mean squared error, and R squared values. These are the metrics we'll be looking at for evaluating regression results. Now, the mean absolute error is one of the commonest that is used for regression, machine learning regression results. And it's pretty basic. Like, you are just trying to, if you look at this plot here, this is where we want our values to be, along this green line, right? And then you now have your predictions kind of scattered around the line. So what this mean absolute error is trying to gauge is how far your values are, your results are from the actual values. So you are taking the actual value minus the predicted value, the absolute value of all the actual. You are subtracting the predictions from the actual value. You take the sum of all the absolute values, and then divide it by the number of values you have, a simple average. And it tells you how well your model is performing. Now, you want your mean absolute error to be low, and this is relative depending on the kind of data set you have. For example, if you are predicting, let's say you're predicting house prices, which is in hundreds of thousands of dollars, for instance, and you have a mean absolute error of, let's say, $50 or $20, that could be acceptable because the prices of those houses are in hundreds of thousands of dollars. So having an error of 20, 50 wouldn't affect the price of the house so badly. So you could accept that as a reasonable error. But let's say you are predicting, let's say, ages of people or percentage results, and then you now have error of 50. Like the total is 100 if you're predicting something that's in percentage, and then you have error of 50, that's too high. Even having an error of 5 may be high, depending on how much on what you're actually predicting. So the value of your error would depend on what your output is, and then you'll be able to tell how much error is acceptable to you, because you're the one creating the model. You'll be able to tell how much error is acceptable to you, but you need to get the error as low as possible so it doesn't affect your model's prediction. So this is a mean absolute error. It's very simple and straightforward, easy to understand, easy to explain. When you have this error, you can easily explain in your results what it means. It's easy to visualize and know what it's saying. But one of the problems with this model, with this kind of error, is that when you have outliers, for example, that are very, for maybe you just have two values that fall very far away from the actual line, they tend to affect your error, your mean absolute error a lot, and give you very high error value. Maybe just one value that falls very far away will give you a very high error. So it kind of outliers easily affect the results you get from MAE, which could be a problem. That's why one of the things we do when cleaning data is also sometimes to remove outliers, because it can affect the performance of our models. So another metric is a mean squared error. In this case, when you take the difference between your actual value and the predicted value, you square it before taking the average of those squares. So like I said before, it's all depends on you. You want to get your error to be as low as possible, but it depends on what you are predicting. So you have to see the difference between the error and the value you are predicting has to be very, very wide, so that you know that this error is not really affecting your output so much. If your error is too high, then you know that your values, the results you are getting, are not right. Okay, so this is a mean squared error. And then the root mean square error is simply the square root of the mean squared error. So all these are different regression metric, evaluation metrics for regression. With this particular mean square error and root mean square error, they're actually less affected by outliers than the mean absolute error. So if you have results that have so many outliers, so many points that are a bit far from the main data, and you need to have them in the database, you could use mean square error, root mean square error to prevent those outliers from actually affecting your errors. Because if you use mean absolute error, it gives you very large errors, and you may think that your model is not performing well. That's why when we are doing machine learning models, you actually use a variety of evaluation metrics. You don't stick to just one. You use all of them, then you compare, and then, because some of them perform better in different situations, which is what you need to check how this kind of metric works with the kind of data set you have. The different metrics work well with different types of data sets. So you need to know that when you are creating your model and evaluating them. So the R-square value is a statistical value. For those who are good at statistics, I think you must have come across the R-square value, which is on a scale from 0 to 1. It kind of works very well for linear regression models, and it tells you how well your model is performing. The closer your R-square value is to 100 or to 1, if you're doing a scale of 0 to 1 or a scale of 0 to 100, the closer it is to 1, the better for you. But you should know that the R-square value is not always the perfect evaluation metric for every regression model, because it works best for linear models. So when you have models that are not so linear, then you may want to look at the mean square error and the root mean square error more than the R-square value. All right, so here we have these are some plots we have from some of the data that we run. You can see this first one here, we have an R-square value of 82%. You see how the data points are more aligned towards the central line than here where we have an R-square value of 54%. We have more scatter. The predictions are more scattered away from the actual fit. So the R-square value actually tells you how well your model is able to fit on the actual predictions. So this table here, we're going to get the slides. This table here actually gives us how to know which model to use, which evaluation metric to use, and when to use them. So you can go through this and look for other resources when you want to use regression to see which of the evaluation metrics is best for the work that you are doing. Okay, then here I have the Python code. Now, when you are running these evaluation metrics with Python, it's not like you really have to code the entire thing. The sklearn already has these metrics already inbuilt. So all you need to do is just to call them. So like for mean square error, you just call this line, and then it will help you to calculate the mean square error from your true values and your predicted values. The same thing with the root mean square error. You just call, once you know the correct code to write, here is mean squared error. Here you have mean squared. Okay, I think it should be root mean square error here. Here you have mean absolute error. So you just, once you're able to write the correct code, the model calculates it and gives you your results. So you don't need to be an expert coder to be able to do this. Once you know the right line to put there, you just call it and then it will do the evaluation for you and you get your results and you're able to look into them and tell whether your model is performing well or what you need to change, what you need to adjust in your model. So the next thing we want to look at is underfitting and overfitting. Now, remember, we are going to do feature selection, but before we do that, we need to be able to understand how to know whether our model is performing well. And then when we know that, we now decide whether the features we are using are okay to be used or we have to reduce them or add more, whatever the case may be. So underfitting and overfitting are also some problems that could arise when you are creating models or developing models using machine learning. Now, underfitting is also called high bias. Now, what that simply means is that if you look at this plot here, you are trying to create a model. Machine learning, you're trying to create a model that is able to understand your data and help you make predictions based on its understanding. It's like you are creating an equation for your data. And that equation is supposed to be able to fit your data to a large extent such that when you change the variables in that equation and bring new variables which were not there, which the model has not seen before, it can give you correct predictions. But when you have underfitting, like for example, now this is if you look at the data set here, it is curved, but the model has predicted a straight line. Now, if you bring new data sets or new points that you want to test, maybe outside the line here, most likely the model is going to predict wrongly because it has a high bias. It doesn't fit well. So this is underfitting where the model does not fit data set properly at all. That means your equation is too simple. It doesn't really understand your data set. So what you want to have is a model that fits your data kind of like this, so that the equation that the model has created, that's a simple way of understanding the model. The simple way of understanding is that your model is creating an equation that understands your data, such that when you bring new values, the model can predict what those new values, what the output for those new values will be. So if you have this kind of equation, if you look at this, it actually fits the data very well. And if you want to predict a new value, maybe at this point, you will discover that the model most likely will give you the correct output. So this is the kind of good fitting that we want to have. Now with overfitting, it's a situation where the equation fits the data too well, such that in between the fitted points, you can see that the model actually bends. It just understands the points that it has seen, but the fitting is such that once you try to extrapolate it, you get wrong values. For example, now, if you look at the trend of this plot, you see that it is going upwards. But this overfitted plot here is actually going downwards because it is the equation that has been created here is probably too complex for the data set. So the fit is just too much. And once you try to predict anything that is outside the points that the model has seen, it gives you wrong values. So you don't want to have overfitting and you don't want to have underfitting. What you want to have is a model that understands your data and follows the right trend of your data. So this is what we call a good fit. This is overfitting. Your equation is too complex here. This is too simple, but this is just right. So underfitting is high bias when the model is too simple to understand the data properly. And overfitting is high variance. The model is just probably too complex and does not understand the data. It just fits too properly to the already seen points such that it cannot predict points that are outside the seen points very correctly. So we want to have good fitting, not overfitting and not underfitting. So this is just another explanation of what overfitting and underfitting would look like in your data set. These are just simple curves to try to explain what they look like. Your data may not be just two variables or two features. So you may not be able to visualize it like this, but there are ways you can tell whether your model is underfitting or whether your model is overfitting. So, okay. So after understanding how to evaluate your model, now to be able to create your machine learning model, I think Dr. Trusten also mentioned this last week. You need to be able to split your data into training sets and testing set. Now, the training set is a set that's going to be used to train the model, while the test set is the one that you will use to test how great your model is. Normally, a lot of people use 80% for training and then 20% for testing, which is the typical approach. But you could vary that based on maybe the amount of your data or what you're looking at. But this is the typical approach that most people use. You split into 80% and 20%. So we'll look at this when we are running the actual models, and we'll split our data set into 80% and 20%. Now, there's something called hyperparameter tuning, which we're not going to look at in detail in this class. But what the hyperparameter tuning is actually for is for you to improve the performance of your model. And in this case, you will need to split your data set into 3 groups. Now you have your training, testing set. So if you want to do hyperparameter tuning, you split your data into 3. You have the training set, you now have the validation set, and then you have the testing set. Now, after your model has been trained using the training set, usually you could do maybe 70% for the training set, 15% for validation, and then 15% for testing. So that 15% for validation is what the model will use to tune. That's what you use to tune your model. And after tuning, you use the testing set to test it. So the validation set is used for tuning. But we'll not look at that now. I think in the subsequent class, we're going to look into that hyperparameter tuning. But I wanted to bring that in here since we're talking about data splitting into training and testing. There's also a situation where you could have 3 splits, where you could have training, validation, and testing set, because you want to do hyperparameter tuning. So the training set is always the largest portion of the data where the machine learning model is trained. The training set is used to train your machine learning model. Then the validation set is used to tune the hyperparameters. As we'll look at different models in subsequent classes, we'll look at the decision tree model, the random forest models. You'll discover that those models have different parameters that make them work. And these parameters can be tuned to improve the performance of the model. That's where the hyperparameter tuning comes in. And you could use your validation set to do that. Then the test set now tells you that your model is, whether the model is performing well because the test set is a data that you keep aside. After you've done the training and validation, then you now test it using the test set. And if you have a good accuracy on the test set, it means that your model is actually performing well. Okay. So now we come to feature selection and feature importance. Now, why do we need to do feature selection? Now, feature selection is a process of choosing a subset of the most relevant features on which to focus for building predictive models. It's very important to do this because it could improve the performance of your model. It could help to reduce overfitting. Sometimes you have overfitting because the features that you have are just too many. So the model just learns them too well, such that it's not able to, it doesn't really understand the model, your data set properly. The features are so many, so it makes the model to have very high overfitting, and it's difficult for the model to be able to work with data set that it has not seen. So sometimes reducing your features, selecting the appropriate number of features would help to reduce overfitting. Then it also helps you to be able to interpret your results properly, and then reduces computational cost. The higher the features you have, the more computing power you need to run your model. It could take longer time. You may need your system, maybe your computer system may not even be able to do it. You will need more power from high-powered computing systems to be able to do the work. So it's very important for us to be able to understand how to select the right features for our model. And there are different methods that can be used for feature selection, which we're going to look at in the next slide. So they are broadly grouped into filter methods, wrapper methods, and embedded methods. And I'm going to explain what all these are. Now, if you look at the filter method, this is basically a statistical approach where for those of us who are good in statistics, you use any statistical metric you are good at to process your data, and then you select the features that are ranked high, that are highly ranked based on the statistical metric that you use, and then you use those features for your model. So filter method is basically you apply a statistical approach. This is not machine learning yet. You just use a statistical approach. I think I'm not really very familiar with statistics like that, but I think there are some kind of like chi-square tests that you can use, or maybe correlation. You use those metrics to test your features and then pick the best performing features based on that statistical approach, and then use them to fit into your model. This is called the filter method. You use statistics to select the features. Then another method is called the wrapper method. In this case, you have a model, you create a model such that it randomly selects different groups of features. Like, look at what we have here. The model could select these 3 features and use them and then do predictions. Now select another set of maybe 3 features, randomly select different groups of your features. It trains over and over. Your model will be trained over and over, selecting different subsets of your features. And then you now select the subset that performs the best. So it's called the wrapper method. So your model keeps doing that over and over again, selecting different subsets, and then you look at the results. After it has selected a good number of subsets, you look at the results and see which subset gave you the best performance, and then maybe decide to go with that subset of features for your predictive model. So you do that, you have to repeat that severally. I think we did something like that. We had to run, sometimes you have to run hundreds of different models, train different hundreds of models to see which one gives you the best subset. Because let's say you have 15 features or 20 features, right? You could train a model that will pick maybe six features, right? And if it picks out of 20 features, you are picking randomly groups of 6. You have a lot of models at the end of the day. So when you get those models, you will now look at the R-square values. If it's regression, you look at the R-square, you look at the mean average error, you look at the MSE, RMSE, and see which of the subsets gives you low errors or high R-square values. Then you may decide to pick that subset and use it for your predictive model. But remember that you have an aim, you have a goal at the end of the day, what you want to achieve with that model. So if the subset that the model selects to give high accuracy or high R-square value doesn't really portray what you want, you may have to think of maybe using another approach, maybe hyperparameter tuning or something else to improve the performance of your model. Then the last one is the embedded model. This is where we use feature importance. So you have your model, you train your model, and after training your model, you now allow the model to pick the most important features. And then you use those important features to train another model. You use those selected important features to train another model. And this may give you higher accuracy. Not always. Like we say, when training a machine learning model, you have to keep trying different things. So, but once you train the model, maybe you have a model that gives you maybe an accuracy of 82% or 80%, and you feel you want to improve it to maybe 90. So you decide to use a feature importance method, allow the model to choose the most important features that were important to its predictions. And you take those important features and then use them to train the model again. It might improve the accuracy of your result. It might improve your F1 score, or it may not. But that's something worth trying to see if you get better output and better results. So that is that about feature importance. So yeah, this is just another approach of looking at feature selection. This still falls under what we have discussed before. So I'm going to skip this slide and look at feature importance. Now, the embedded method we just looked at, the last method on feature selection, actually works more on feature importance. And I want to explain what feature importance is here. So feature importance basically refers to the measure of impact, or how important the feature is to the predictions of your model. Now, if you are predicting house prices, for instance, and you have features such as the size of the house, the number of rooms of the house, the number of square feet the house is, the what else could be there? Maybe the number of baths and toilets in the house and all that. So you want to know which of these features were most feature that for the prediction of your model. You may end up saying that maybe the number of toilets or the number of square feet of the house is not as important as the number of rooms. So the feature importance actually helps you know which of the features was more important and impacted your model's predictions the most. We need to do this sometimes because it helps you to create a more reliable model. And then you can also tell if your model is working well. Take, for instance, now you are trying to predict let's look at the house price, we're talking about. And then your model now, maybe you have a very, which feature could I use that is unimportant, that is not so important? Or maybe you can look at something like, well, I can't really think of an example right now, but there's some features, based on the work that you are doing, that this feature is actually something that shouldn't really affect your result. And then if you do a feature importance and that particular feature now begins to show as the most important feature, then you should check something may be wrong, either with your data. Maybe you didn't normalize your data, you didn't scale it well, so that the model is beginning to pick something that shouldn't be important, because you actually have domain knowledge is very important. When you're doing machine learning, you understand the domain within which you're working. You have good knowledge of your data sets and the parameters you're working with. So you know that certain things may not shouldn't have very high importance more than others. So if you create a model that begins to give you something that is quite inconsequential, and the model makes it very important, then you have to check. Something may be wrong in the way you process your data, or something may be wrong in the scaling, the normalization, or maybe your data something may be wrong. So it helps you to check the reliability of your model. The model may not be working rightly. That's why you may be having something that shouldn't be important, giving you high feature importance. Then it also helps you to select features. When you do feature importance and you want to do feature reduction or dimensionality reduction, the feature importance could help you to know which features to select and which ones to drop. Then it can also help you to dig deeper. You can do feature importance, and it helps you to dig deeper into the predictions of your models. You can help you to do, you can use the feature importance as a way of analyzing your model's predictions and discussing your results. And it could give you some great insights into your data set and into the models that you have created. So feature importance is very important. And we're going to do some, run some code that will show us what the feature importance actually looks like. So this is just a sample Python code for a machine learning model on how to do feature importance, but we'll run an actual code after this. So dimensionality reduction is a process of reducing the number of input variables as the features in the characteristics. And we can use feature selection to reduce dimensionality, that's to reduce the number of features. But having a large number of features sometimes could lead to overfitting in your model. So you may want to, at some point, reduce the number of features you have, but you have to be careful because it could result in you in losing some data. It could reduce your accuracy. There are times actually that you select features and your accuracy drops. So you have to balance between whether you need to reduce the features or you use all of the study about what you're working on detailedly, so you know when to choose whether to reduce features, to use all of them, or what needs to be done to improve the performance of your model. Because there are several things you can try, but you have to be careful not to you need to be careful to preserve the essential characteristics of your data so you don't lose valuable information just because you want to reduce the number of features in your data set. Okay, so now we're going to go into training a simple machine learning model, and we'll look at those features that those evaluation metrics that we have discussed, and we'll see how they actually play out when you're running a real machine learning model in Python. These are the practice questions that I have for this class, for those who join online. I have 4 questions here. Which of the following best describes overfitting? Okay. So I think I didn't explain this part in the class. So to be able to tell whether your model is overfitting, you have to check both your training data and your testing data. So if you have the accuracy from your training set and the accuracy from your testing set, now if both of them are low, you know that your model is poor, it's underfitting, because your model cannot even predict well on the training set, not to talk of the testing set. So when your accuracy from both your training set and your testing set are low, you know that you have underfitting. And that is not what we want to have in our machine learning model. Then, when you now have a high accuracy on your training set, and then your testing accuracy is low, then you know that that's overfitting. Means the training data overfit the model and it has a high accuracy. But when you bring new data to test the model, then you now start having low accuracies. That's called overfitting. So the answer to this question 1 is actually when your model performs well on training data, but poorly on testing data, then you know that your model is overfitting. Yes, overfitting. So to tell between overfitting and underfitting, you have to get the accuracy from your training set and the accuracy from your testing set and compare them. If the accuracies are low from both ends, then you know that your model is underfitted. But if you have high accuracy for training and then low accuracy for testing, then your model is overfitting. And then you have to do one of the things we have discussed or what we'll discuss in future classes to see how you can improve the performance of your model. So these are the questions for those who check online. I think we should be able to answer this if we have gone through the class. So I'll stop sharing and then share my Jupyter notebook so we can go through the model. So I think I can take questions here while I try to share my Jupyter notebook. Thank you for listening.
Yes.
Hello.
So at this point, if you have any question, please go ahead.
Hello.
Yes, I can hear you.
Yeah, good evening, Doctor. My name is Mohammed Kamara from University of Liberia. Thank you for the brilliant explanation. But I just want to take you back to accuracy, where you mentioned that for the accuracy, you have series of data. If you want to know how accurate your data is, now, I would like to know from you, in finding the accuracy, it said that you are going to test each of the data, or you are going to add all and divide by the total to find the accuracy of the entire data, or it just you are going to test bit by bit? That is the question.
Okay. So with accuracy, like I showed you the equation. So the model is actually the evaluation metric, you're going to call it. The sklearn has those metrics already embedded in it. So you call the accuracy metric.
It's
And
sounding
what it
low.
does
I'm
is to
not getting
calculate.
you.
Okay. This can, okay, let me speak louder. Can you
Yeah.
hear me now?
Yeah.
All right. So what I was saying is that, yeah, so the metric is already in the sklearn, which you're using already. So once you call the accuracy metric, what it does is to calculate the total number of correct predictions over your total predictions, right? You are not the one calculating it. The sklearn metric does it for you. So it's calculating everything. It will collate it for you. You get that?
Okay.
Yeah.
Yeah, I get it now.
I hope I answered the question. All right.
Yeah, I get it.
Any other question?
I thought you were going to test them
All right. Thank you.
individually.
So the model will do it for you. Once you call the accuracy metric, it will do that for you to calculate everything for you. Same with all the other metrics.
Okay.
All right. While I wait for other questions, I think I'll just go ahead with looking through the Jupyter notebook. I hope you can see my screen clearly. So this is a simple classification model. We'll look at a classification model and we'll look at a regression model, just simple machine learning models that will help us see and visualize the metrics that we just looked at. Now, we're looking at the iris data set. The data set that comes with the sklearn, which you have already installed in your systems. So you have this already. So it's actually a flowers data set where they are trying to predict different species of the flower using their sepal length, sepal width, petal length, and petal width. So this data set actually has 150 data points, and it has 4 features, which are the sepal length, sepal width, petal length, petal width. And then it wants to predict 3 classes. And each of those 3 classes it's a balanced data set. So each class has 50 records in the data set. So it's quite balanced between the 3 classes. So it's a model data set that comes in the sklearn. So this machine learning model, which I have here, let me see if I can zoom this out, okay, to make it clear. Yeah. So first we call the data set, we load iris, which is data set, and then we also import our train test split, which will help us to split our data set into 80% for training and 20% for testing. Then we're going to be using the decision tree classifier. I think in subsequent classes, we'll learn more about what decision tree model is and how it performs. But today we're just going to use it's a simple model, a tree-based model, which we'll look at later. And then we want to look at accuracy score. I think this is what somebody just asked me, Mohammed just asked about now. So we have loaded the data set and we have assigned X values and Y values as a target. And this target value, like I said before, we're trying to predict one of these species, whether it's Setosa, versicolor, or virginica, right? Okay, so if you look at this line here, we have split the data into, okay, here is 0.3. That means we have split it into 0.3 for testing. That's 30% for testing, and then 70%, but I could change this to 2, which will make it 20% for testing and then 80% for training. Now, this random state helps to, once you put a random state and you keep using the same random state, each time you run the model, it will keep giving you the same result. But if you don't put the random state here, each time you run the model is likely to probably give you different outputs. So we call our model here, which is a decision tree classifier. Then we fit the model for the training, X train data, Y train. That's the 80% which we have kept for training. We use it to fit the model here, X train, Y train. And then here, this step now is to make predictions, right? Which will be where our model will be getting its accuracy from. So after doing that, look at this. You call your accuracy from the question which I just answered. Once you call accuracy here, you call accuracy score. The model is now going to evaluate performance based on the y-test values, right? The actual y-test values. No, your test set is 20%. So based on the actual testing values and then what the model was able to predict. So the model is going to calculate it for you based on how many of the predicted values were actually correct out of the, as in to compare the predicted values with the test values and tell you how many % were actually correct. So since we have gone through the code, I'm just going to press Shift Enter to run it and then to give us the results. Yeah, so you can see it gave us more accuracy of 1. Now this is a standard data set which came with the SK lens. So we can understand why the accuracy is 1. It's a very balanced data set. And yeah, so we have a model accuracy of 1. So it means the model we should assume that it's a very good model, right? But now we want to go further to use other metrics to test our model to see whether our model is performing well. So okay, right. This is still the same thing I just ran before. I think what I just included here was to include a line to show us the head of the data so we can actually see what the data is about. So still the same thing. There's nothing extra here. So we can see what the model looks like. We added a line here, df.head, to show us the head of the data, the first 5 entries of the data. So we can see sepal length here in centimeters, sepal weight in centimeters, petal length. This gives us an overview of what the data looks like, and the accuracy is 1.0. Okay, so now I want to add the confusion matrix. So remember the other time I just called only accuracy score. If you look at the other code here, I just called accuracy score. But here now I'm going to call confusion matrix and then confusion matrix display so that we can actually visualize the confusion matrix. And then I call matplotlib to be able to help us plot the confusion matrix. So I think in the class we did on Python, we explained how we can use matplotlib for plotting our results. So everything here is the same. The only thing that is different is where here I call the confusion matrix. So the confusion matrix here is still going to be comparing the test data and the actual test data, which was the data we kept, the 20% we kept, and the predictions that the model will make. So we're going to see how well the model performed. So based on the accuracy, we should be expecting that the confusion matrix should be quite good. So let's run this. Press Shift Enter here and see what it will look like. And you can see we had a very high accuracy. And you can see the confusion matrix, right? Along this diagonal, we have all the values here and we have zeros in the other side, which confirms the 100% accuracy that the model had. So where we have Setosa 19, the model predicted it correctly. Where we have versicolor 13, the model predicted them correctly. The same thing with the Virginica. You see the model predicted it correctly. So this is what so what you simply need to do is just to call your confusion matrix and feed the test data and then see how well the model is able to predict. Okay, so let's look at the feature importance from this particular data set and see what it will look like. So if you look at what this first part where I'm importing libraries, So here we import numpy as NP. We imported the usual things that we needed, right? So then if you come down here, look at the feature importance line. So we have this line for importances. So we have model.feature importance. This is what tells the model to calculate the feature importance. So you are calculating the feature importance of the model that you just trained. Here you want to know which of the features. Remember, we have 4 features: sepal length, the petal length, the sepal width, and petal width. Those are the 4 features we have in this model. So out of these 4 features, you really want to tell which of these features impacted the model's prediction the most, which was the most important feature that makes the model to predict the way it does. So this is for plotting the feature importance, because your feature importance could be given to you as figures. It could also be given to you as a bar plot. So here is the plotting of the feature importance. So I will just run this. I think we'll make all this available to you at the end of the class, so you can try running them and go through them to understand it better. So I press the shift enter. So you see the feature importance was given here in figures, right? For the sepal length, it has a 0 feature importance, telling us that the model doesn't even attach any importance, so it doesn't even affect the model's prediction. This should actually mean that if you remove the feature importance, this sepal length, the model may still have its full accuracy and will still work effectively without the sepal length. So then we have the next, we have the feature importance for the sepal width, for the petal length, and for petal width. So when you put in the bar plot, you can actually visualize it easier. So you can see which of the features actually impacted the predictions of the model more. Now sepal length was 0, so you can see that this is 0. And we could actually maybe understand that if you look at the sepal of flowers, that green part at the bottom that holds the flowers, maybe all of them have almost the same length. So if they're almost the same, it might not affect the model's predictions. Maybe the sepal length for all the flowers are almost the same. That's why it's not really affecting the model predictions. So that could be one of the reasons. But when you understand the domain, you understand your data set, you understand what you're working with, you may be able to explain why the sepal length has a 0 feature importance. So that depends on the data set that you're working with. Now let's look at regression. So I think we've looked at confusion matrix and accuracy for classification. Let's look at some other examples from regression. Now, this is the California housing data set. It's still a data set that is found within sklearn. So we are going to try to look at the data set. This is a larger data set. It has 20,640 data points. It has eight features, which include the age of the house, the average number of rooms, bedrooms, the population of the area where the house is located, the average occupancy, latitude, longitude. So we want to see how we can visualize our R-square. We want to see the mean average error, MSE, from this data set. So I'm using a linear regression model. So you can see here where I'm calling the model. First, I call the California housing data set here. Then I call my trained test splits, called linear regression model. Then I call all these different metrics: the mean squared error, the mean absolute error, and the R-squared score. So remember that this housing data set is actually to predict house prices, right? To predict the prices of the house. So we'll look at the output we get and see whether it makes sense, whether the errors make sense, and whether the errors are too high or they are too low based on the data set. So, okay. So let's look at the code that we have here. So we call the data set, we set the X and Y values. We now split the data. Here we have 0.3. Let me change it to 2. So that means 20% for testing and then 80% for training. Then we call our model, which is the linear regression model. Then we fit our model with the training data. And then here, this line is for the predictions using the testing data, just the X test. And then based on the predictions, or you feed the X test into your model and it to predict values for you. So the value it predicts will now be the Y predicted. Then the actual Y test values will be compared with the predicted values. So we're going to look at the mean squared error, the mean absolute error, and the R-squared score. So let's run this and see what we get. Press Shift Enter here. And we can see the mean squared error here is 0.55. The mean absolute error here is 0.53. Now remember that this data set, let's look at what is. This house prices are in thousands of dollars. So in hundreds of thousands, right? So whatever error we get here is like 0.55 times 100,000. So if you multiply 0.55 times 100,000, what does that give us? That's like 55,000. That's giving you an error of about 55,000 in, you're trying to predict a house price and you have an error of 55,000. Is that an error you want to accept? That's a large amount of money, $55,000 error in predicting house prices. That's a very high error. And I don't think you want to accept that kind of error in making predictions of house prices. And we can see that the R-squared score here is 0.5, which is also low. So if we compare the error, the mean absolute error, we're having an error of about $55,000. We're having R-squared score of about 0.5, which is quite far away from 1. So we can see that it's actually not performing well. So there may be ways you may want to improve on it. First of all, this is a linear regression model, so it's a very linear model. Maybe it's just not the right model to use for this data set. Or maybe you have to do hyperparameter tuning, or maybe you have to select some features. Maybe there's some features that are really not important, which are affecting your model's predictions. So what we are doing here is to just give you knowledge of different things that you can try based on what you're working with. You can decide, okay, maybe I try another model. Maybe I reduce the features. Maybe I tune the parameters of the model I'm working with. So you can try different things to try to improve and create a better model that will give you better predictions and better outputs for the work you are doing. So from here, we can see that this model didn't work well. It's either the model didn't work well, but I think with this is a model. So maybe if we try the different model, we get better errors, lower errors, and higher R-squared score. So knowledge of a database and the target helps you with deciding if the error is acceptable. So once you know your database very well, it will help you to decide whether the error you have gotten is acceptable or you have to work on it. So here, I think I tried to print the head of the data set so we can have an idea of what the data set looks like. And then let me do that. So look at this now. So this is what the data set looks like. This is a target. Now look at this. Your target is the target here. Look, you have 4.5. This 4.5, remember we say it's in hundreds of thousands of dollars. So this 4.5, you multiply it times 100,000, which should give you like, right? That'll give us like 450,000, right? Thereabout. So if you're having a house price of 450,000 thereabout, and then you're having an error of $55,000, I think that shouldn't be an acceptable error. It's too high. So the model needs to work. So this just gives us an overview of what the data is. The data looks like it has 220,640 data points and 8 features. And this is still the mean squared error, the absolute error, and the R-squared value for this data. So it's low. And I think it needs to be improved on, and that can be done through several methods. So we can also visualize the results of regression. We're able to visualize the confusion matrix in the previous example we looked at on classification. Same with regression, you can also visualize it. So I've included plotting here where you can plot your R-square value. So let me plot that so you can see. Now you can see the trend in the data, right? This is what the actual value is supposed to look like. But you see that the data points here, and the model just doesn't work. That's why we have a low R-square value. The predictions and the actual don't align. So that's why the R-square score is quite low. So we need to be able to improve upon the model or choose another model that will better fit the data. So this is a bar plot for R-squared score. Now this is just one R-square score. That's why it's just a lone bar plot here. But if you had maybe several models, like let's say you decide to use linear regression model, random forest, XGBoost, and any other model, now you can get the code to plot the R-square values in one plot, and then you'll be able to compare them. Just by mere looking, you can tell which has a higher R-square value and can help you to pick the best model if it's R-square score you want to go by to evaluate your results. So this is just to show you that you can actually plot your R-square values in the bar plot and then compare different models together. So yeah, I think I've come to the end of this code. If we have any questions, you can ask, but I'll share this code and it will be posted for anybody that wants to go through it. Thank you very much.
Thank you, Dad. Yeah. I just want to ask a short question.
Yes, please.
Yeah, this other workbook, is it in our Jupyter? Can we find it in a Jupyter notebook? This identical coding that you talk about, you presented on.
Which one?
The one that I'm seeing now, the one that on the screen.
Oh yes, this is my Jupyter notebook. I created the Jupyter notebook and I will share it. So in case you need it, I can share this so that you can use it here.
Yeah, because we don't have it, so our concern, that's all. Are you hearing me?
Yes, Mohammed. Yes. So it will be shared and then you will get access to it. I think you're also missing the notes on the Python. I'm trying to get it from the teacher as well. He was trying to make some changes, so I'll get that as well to you. So all these documents will be posted in the WhatsApp group, and I'll email them to you as well. So everybody will have them. But if you have any questions for the teacher, if you send them to me, I'll get the teachers to respond to you as well. So thank you very much, Benis. This has been a wonderful session. And we really appreciate the time and effort that you have put into this. So we are going to end our class here. Next 2 weeks, we'll be coming back with another session. And I hope everybody will be ready for that. Next 2 weeks, we are going to do supervised learning. Now we are entering the machine learning proper. So we are going to do supervised learning that will also take care of decision tree, KNN, and other stuff, regression and random forest, unsupervised learning. We're also going to look at that. So next week is the real machine learning. You are deep in machine learning. Next 2 weeks, I should say. So next 2 weeks, that is on the 10th of October. Let's all try and come around. We are trying to put together a presentation for you next week. If the resource person is still trying to give us some time. If we get that time, we'll post it in the group so that next week you would have a general presentation, but the next class will be next 2 weeks where we'll be looking at supervised learning. And that is the real machine learning. So if you have been coming and you missed that one, you will miss the real machine learning process. So thank you very much, everyone, for making time to be around. I would stay around to answer any questions you have on WhatsApp. And thank you very much. We'll post this video on the website. We'll post this video on the website, and we'll also post the link in our various groups so that you can get access to it. Thank you very much. God bless you. See you next 2 weeks.